In our final section in this unit, we're going to talk about exponential and logarithmic equations. So we spent a ton of time worrying about dealing with these properties. We've seen a bit involving equations, but now we just kind of want to take a general approach. How do I tackle solving for x if it involves the x being in the exponent position or if it's inside of a logarithm? So the most useful thing that's going to happen or help us is going to be from that one-to-one property that both of these functions have. So because they're one-to-one, they both pass the horizontal line test, but what that means is no inputs, different inputs will give you the same output. So if I have something like b to the x equals b to the y, the only way this can possibly happen is if the exponents are equal. So what I want to do when I'm dealing with an exponential equation, my first step is to try to see, can I write both of these sides with the same base? Because if this is the case, then I can say these exponents are equal. So solving this equation would result in x equaling 4, because the exponents would have to equal. We get to ignore that base part then. And the same exact thing is true with logarithms. If you have log base b of something equals log base b of something, the only way this can happen is if the insides are the same. So in the case when we're dealing with a log equation, hopefully we can get log base whatever, so in this instance log base 2 and log base 2, to then say that these insides have to equal, and so we would get x equals 7, okay? So when you're dealing with an exponential equation, your first goal is to try to write things with the same base and then set the exponents equal. Or if I can get the same log on both sides, then I can set the insides equal. If you can't go about this, then what's going to be helpful is trying to switch to the other form. So turn the exponential into log or log to exponential. But the number one thing you have to remember, this little extra parenthesis here because I forgot it, is that log of 0 and log of a negative number are undefined. So once I get equations when I'm dealing with so anytime that we're dealing with a log equation, we have to make sure that we check our answers because we want to make sure that it doesn't cause either of these issues. Right? So really the best thing we can do is just try a ton of examples. So for this very first one, we want to solve the equation exactly for x. Pretty much all the time you're going to want exact. You are going to see in your homework that I will ask you to approximate stuff, but that's what you use the calculator for after you get an exact solution. So don't try to approximate within it. Get the full thing, then plug it into your calculator. So my goal in this first problem is the x value I want is in that exponent position. I want to try to write both sides with the same base. So I have 4/5 here. I want to see, can I maybe write this side as 4/5 to a power? So we're going to have to do some manipulation. So can't do anything with this 4/5 to the x. However, 125 I can write in terms of 5. That's 5 cubed, and 64 is 4 cubed. Okay. So really at this point I have the 5 and 4, but they're in the wrong spot. The 4 needs to be in the numerator, but it's currently in the denominator. And the 5's in the denominator here, but the numerator up here. So what we can actually do is use our exponent property. And if we want to switch the positions, we just make the exponents negative. So the right-hand side is the same thing as 4 to the negative 3 over 5 to the negative 3. And now, because these both have the same exponent, we can take that out. So the left-hand side is still 4/5 to the x. The right-hand side I can write as 4/5 to the negative 3. So we're kind of using those properties in the reverse way. We're used to distributing it down. We're used to turning a negative to a positive. Now I did the opposite to get there. But here, because I now have 4/5 to a power equals 4/5 to a power, it forces these two exponents to equal. So immediately the value of x that solves this equation is x equals -3. Okay, and that is our solution. You can plug it back in at the beginning to see if it works, but it does. Right? For this next one, we have log base 2 of 2x equals log base 6 of x plus 8. We are sitting real pretty because I have log base 6 on both sides. So the only way this equation can be true is if these two insides equal each other. So we would need 2x to equal x plus 8. And then to solve this, we got to get the x by itself. So we subtract x from both sides, gives us x on the left and just 8 on the right. And so we have a solution to our equation. The only thing is, because I dealt with a logarithm, I do need to check because there is a good chance you can get extraneous solutions. So I want to plug in x equals 8 to make sure I don't have any issues. So this gives us log base 6 of 2 times 8. No problems on the inside there. 16 is in the domain of a logarithm. And then on the right-hand side, this is log base 6 of 8 plus 8. So both of these insides are good, and that is really all that I'm checking, that it doesn't cause log of 0 or log of a negative number. So this is our solution to the equation. Okay. So this is what I want to happen every single time. But of course, it's not always going to be that simple. We might have to do some manipulation, or I might not be able to even get the same base on both sides. And this next one is a kind of a prime example of that. So I have 7 to a power equals 15. There is no way I can easily write 15 as 7 to a power, okay? So you have a ton of different ways you can approach this. Really kind of a personal preference, what's up to you, but all of these forms are going to be acceptable. One thing we could do, because it's got the x value in that exponent spot, I could take natural log of both sides to bring the exponent down. The other thing that I think is a little bit simpler is I need to get that exponent down. I can't write this as the same base. Let's put this in log form. So when we do that, our base is 7, our answer is 15, and our exponent is 3 minus 2x. And this log base 7 of 15 is just a number. That's all. So all I need to do to solve for x is get rid of these two numbers in front of it. And the way we would go about that is we would subtract 3 from both sides. I'm just not able to actually condense this. It'd be log base 7 of 15 minus 3 equals negative 2x. And then to get the x by itself, we go ahead and we divide by negative 2. And so really it would just flip this. It would make it negative log base 7 of 15 plus 3x. You can switch it if you want to, or you can leave it as is. I'm going to go ahead and reverse this and write it as 3 minus log base 7 of 15 over 2. And that is equal to our value of x. And this is just a number, okay? You could plug that into your calculator to get a decimal approximation, but I'm also going to show you how to manipulate this so you can see a different form. So a second approach that we could do is to be able to bring this exponent down, we go ahead and we take the natural log of both sides. So this gives us natural log of 15 is equal to natural log of 7 to the 3 minus 2x. And one of our properties about natural logs, or logs in general, is that our exponents pop out. So we can actually bring this down, and this is the same as saying natural log of 15 is equal to 3 minus 2x times natural log of 7. Okay. And then from here, to get the x on its own, I want to get rid of this constant. So I can go ahead and divide this side by natural log of 7, which is exactly what I would have to do over here as well. So on the left-hand side, we have natural log of 15 over natural log of 7 is equal to 3 minus 2x. Okay. And honestly, I want to take a look and compare this equation to what I have right here. They really are exactly the same. So the right-hand side on both of them is 3 minus 2x. The only difference is this is log base 7, and this is dealing with natural logs. But that just comes from the change of base formula. So it's really the same thing. It just looks slightly different. Okay. And then from here, you would go about solving it exactly the same way. You subtract 3. I can't actually subtract 3, so it would just be natural log of 15 over natural log of 7 minus 3 equals negative 2x. And then we go ahead and we divide both sides by negative 2. And that would again switch the order. This would be 3 minus natural log of 15 over natural log of 7, all divided by 2. And that is our value of x. Okay. You might have some issues actually plugging this into your homework software, but you can, again, rearrange this a little bit more. So this would be perfectly fine if you had entered it on a test. It would accept your answer. If it doesn't, contact me. But otherwise, what we can also do to kind of get rid of the fractions within the fractions is we can go ahead and we can multiply the top by natural log of 7, which means we've got to do the same thing in the bottom, multiply by natural log of 7. So this would leave us with 3 natural log of 7 minus natural log of 15 divided by 2 times natural log of 7 equals x, because it would make this cancel when you distribute it out. Okay. So again, both of them work exactly the same. Completely up to you as to which method you want to choose, and you should be good entering this one as well. And again, if it doesn't, let me know, and I'll be happy to correct it for you. All right. So let's try another one of these, because again, I think these tend to be the most complicated of the exponential equations. So we have 4e to the 2x plus 1 equals 17. So here, I don't have it yet where I have just an exponent equals a number. So before I can transfer this into its log form, I've got to get the exponential part by itself. And so the way we can do that, my iPad's going to look crazy, there we go, is we want to just get rid of that 4 through division. So we're going to divide both sides by 4. And this gives us e to the 2x plus 1 is equal to 17 over 4. Now I can rewrite this in its equivalent log form. We have log base e of 17 over 4 equals 2x plus 1. But really, log base e is just natural log. So this is natural log of 17 over 4 equals 2x plus 1. And then to get x by itself, we've got to subtract 1. So this is natural log of 17 over 4 minus 1 equals 2x. And then finally, we're going to go ahead and divide both sides by 2. So our x that solves the equation is natural log of 17 over 4 minus 1 divided by 2. Okay, so this is our value of x that solves the equation. And again, you can plug this into a calculator to get your decimal approximation. But typically, we're going to want the full answer. All right. So we just got a couple more. We haven't really done any log equations yet. Those have just been exponential. We did one small one, but definitely want to go through some more examples with logs. So again, number one thing we have to do is we have to check our answers. So in this case, unlike one of our other ones, I cannot write the right-hand side involving a logarithm. So there's no way I can set the inside of my logs equal. So in this case, when that happens, I want to put it in exponential form. So using our bacon and eggs, our base is 2, our exponent is 3, and our answer is 3x minus 1. Okay? So converting it to exponential form gives me an equation that's actually much easier to solve, because 2 to the third is just 8. So 8 is equal to 3x minus 1. And so from here, we just have a linear equation that we have to solve. We go ahead and add 1 to both sides, and that gives us 9 is equal to 3x. And then we go ahead and divide both sides by 3, and that gives us 3 is equal to x. Okay? So I get a solution. I hope it works, but I do need to check because it was a log equation that we began with. So if we plug this in, that gives us log base 2 of 3 times 3 minus 1 equals 3. And again, I'm not checking to make sure that it works, but more so checking that this is inside the domain of the logs that are given to us. So really on the inside, that would be 9 minus 1. I don't need to condense that. This would be log base 2 of 8. 0 issues with that. That is defined. So this is our solution to this equation. Okay. All right. Now for these next couple ones, we get a little bit funkier purely because we have a lot of logarithms going on. So I can't set insides equal because I don't have log base 2 on the left equals log base 2 on the right. So unfortunately, I've got to do a little bit more work before I can set insides equal. And this is where our log properties are going to come super into play. So we did that condensing of logarithms and expanding. We're going to be able to condense these two. So we want to condense this side to a single log. So because we're adding the two, it will end up becoming multiplication of their insides. So we get log base 2 of x plus 1 times 4 minus x equals log base 2 of 6x. And now because we have log base 2 of something equals log base 2 of something, we can go ahead and say that this inside must equal this inside for these two things to be true. So x plus 1 times 4 minus x needs to equal 6x. Okay. So ultimately, we end up with a quadratic equation that we have to solve. So to be able to factor this fully, remember we need 0 on one side. So unfortunately, we are going to have to FOIL this expression out. So if we do the first terms, we get 4x. If we do the outer, that's negative x squared. The inner is plus 4. And then the last term is minus x. And that equals 6x. Okay. So condensing the two like terms and then putting things in the correct order. This is negative x squared plus 3x plus 4 equals 6x. Okay. So we're super close. I still have to get 0 on one side, so I'm going to go ahead and subtract this 6x over, and that gives us negative x squared minus 3x plus 4 equals 0. So at this point, you're more than welcome to factor. Me personally, I hate having a negative number on that x squared term. So I'm going to go ahead and multiply this entire equation by -1 to really just flip all of these signs. So it becomes x squared plus 3x minus 4 equals 0. That just makes it a little bit simpler when I go to set up my factoring. My first terms have to be x and x to give us x squared. To get the last to multiply to -4, we can do 4 and 1. 1 has to be negative and 1 has to be positive. So we can try this route. This would give us an inner term of 4x minus 1x, which indeed lands us with 3x in the end. So we end up with two solutions. We get -4 and +1. Okay? So it's really simple at this point to say, okay, I've got solutions. I am done. But if you go about that, you're going to end up getting your answers wrong on your homework and potentially your test, because we've got to check both of these solutions. So let's start with x equals -4. Let's see if this one works. So I have to plug it back in to my original equation. So this would give us log base 2 of -4 plus 1. Honestly, without even going further, I can stop here. This gives you log base 2 of -3. And that is a problem. So I don't need to move any further. This solution is no good because I cannot take the log of a negative number. However, if you do want to see the full thing out, it does cause an issue on the other side as well. So this would be 4 minus -4. And on the right-hand side, we'd have log base 2 of 6 times -4. So we run into two issues. That would be log base 2 of 8, but this would be log base 2 of -24 over here. So this is an issue, and this is an issue. We cannot take log of a negative number, so this is an extraneous solution. Yes, it solved the resulting quadratic, but no, it does not solve our actual equation. Right? Hopefully then, at least this one works. So if we plug in +1, this would be log base 2 of 1 plus 1. So that's good, log base 2 of 2. Then we have log base 2 of 4 minus 1. Again, no issues there. And this is log base 2 of 6 times 1. Also, no issues there. So these three work, which means x equals 1 is the only solution to this equation. So I just have one more example to go through. Again, best thing you can do is just practice, practice, practice. Try as many problems as you can. We pretty much want to get a single log always on one side or both sides of the equation, or we want to turn it into that exponential form. So here, because we have this 1 on this side, I'm not going to be able to just set insides equal. Instead, I'm going to have to turn it to exponential form. But before I can do that, I need a single log on this side. So since we do have subtraction of these two logs, remember subtraction turns to division. So this is the same as log base 3 of 10 minus x over x plus 2 equaling 1. Okay? And now I have a single log equation that I can put into exponential form. So our base is 3. Our answer is 10 minus x over x plus 2. And our exponent is 1. Right? So really 3 to the first is just 3. This is 3 is equal to 10 minus x over x plus 2. Right? Now to actually solve this equation, I got to get rid of these fractions. It's a rational equation. So I've got to go ahead and I've got to divide or multiply by this denominator to make these two cancel. And so this leaves us with 3 times x plus 2 is equal to 10 minus x. Distributing that 3 gives us 3x plus 6 is 10 minus x. And now I just got some rearranging. We can add the x to this side, and that gives us 4x plus 6 is 10. And then we can subtract the 6 to give us 4x equals 4. So finally, dividing both sides by 4, we end up with a single solution of x equals 1. Right? But again, always got to check because I started with logs. So if I plug in x equals 1, this gives us log base 3 of 10 minus 1. Great, no issue there. And this is log base 3 of 1 plus 2 equals 1. Also, no issue there. So this is our solution to the equation.